first one is the fluid flow source. One example is depicted right here. It's basically just a syringe. So you push this up and you provide a volume flow. And this is why it's called fluid flow source. It acts as a flow source and it provides a volume flow. And if you press this constant, you have constant volume flow. So the volumetric flow that is provided by such a source is independent of the chip. If you imagine that you have a chip with different channels, or different length of channels, you can expect those channels to have different kinds of fluidic resistance. And if you attach a flow source, the flow source will be the same within those channels. So it's independent of the chip geometry. The volumetric flow rate is defined by your source. But in contrast to that, the generated pressure, of course, then depends on the chip resistance. So if you attach a very large channel, or if this channel is very large, and you want to achieve a given flow rate, then you don't have to apply much force. But if this is a very small channel with high resistance, you have to apply quite some force to achieve the same flow rate. And the second type of external sources are pressure sources. Those, as the name suggests, act as a pressure source, and it can be realized like this. So you also have like a reservoir, and then you apply a constant pressure here, and this constant pressure is going to push your liquid in your microfluidic system. And here the pressure which is applied is independent of the chip, so you always have the same pressure at the inlet of your chip, and thus the generated flow rate depends on the layout of your microfluidic chip. And basically all external sources can be classified as either a pressure source or a fluid flow source. And here are some examples. So one, for example, is just a constant pressure source, which could look like this. So it could be any kind of pressure cartridge. If you put a valve on it, it would be even controllable. And sometimes small versions are even embedded in the chip system, and you just push them with your finger, then they break, the seal breaks, and you have pressure. But it can also be external, of course. And the second one looks like this, and this is the classic microfluidic external pump. And as you can already see in this image, those pumps are, well, they are external, so they are convenient. You can program them to fulfill many different tasks. But you can see that the whole setup overall is quite large. You can see that you again have the problem of those macro to micro interfaces. So how do I get from the tubings of this macro pump to my micro channels? And as you can already see, with those tubings you have a lot of dead volume. So if you imagine you have a channel which, if you want to process maybe a couple of hundred nanoliters, and for example your reagent is very costly, then you would not use such a system where you have to fill several milliliters into those tubings just to provide the flow. Alright, and before we look into more applications, I quickly want to remind you of some basics we covered in this course, and we start with pressure-driven flow. Does anybody of you have an idea? Can you name one or two characteristics of flow in pressure-driven microchannels? What comes to your mind if you hear characteristics of flow in microchannels, of pressure-driven flow? Sorry? Turbulent. Well, in microchannels, we don't have turbulent flow.